Hi, Mike here, and we're going to talk about probability distributions. And this comes right after random variables, and there's some very famous probability distributions that are used a lot. There are a gazillion different types of random variables. They're discrete, continuous, and to specify a random variable, you just have to specify the values x takes on with what probabilities. But there's some that occur a lot in nature, some that people go to time and time again, the model phenomena. And the most popular one that's discrete is called the binomial. And the most popular one that is continuous is called the normal. And there are other ones. There's the geometric, there's the Poisson that you can study. But really, if you know the binomial, you know the normal, you know the two most popular distributions out there that we go to time and time again. So right now we're going to talk about the binomial distribution. So the binomial distribution means you're doing something n times. You're shooting free throws. You're flipping a coin. We try to think of flipping a coin a lot when we do the binomial because it's the classic setup. You're doing something n times. Each time you do it, there's only two outcomes, success or a failure. Julie's working hard tonight. Look at that. I don't know how to dismiss that. And then the probability P of success stays constant for each trial. So you're doing something n times. Each time you do it, there's success or failure. The probability of success is P. The probability of failure is 1 minus P. And our interest is in the total number of successes out of n trials. So X is the number of successes out of n trials. I'm not even going to try to write the word successes. And what can X take? X can take on the value of 0. You saw no successes. 1, 2, up to n. All successes. And we want to model X. We want to model the number of successes on n trials. And that's called a binomial random variable. As an example, MSA Electronics experimenting with the manufacture of a new transistor, a piece of electronics. And every hour a random sample of 5 transistors is taken. The probability of one transistor being defective is 0.15. What's the probability of finding more than 3 defective? That's the classic binomial setup in quality control. The probability that any particular customer who visits Zappos makes a purchase is about 0.2. Assume that visitors make their purchase decisions independently. What's the probability that no more than 10 of the last 50 visitors make a purchase? This, you could argue, may not be true. What if you're sitting next to a coworker or a friend and you're shopping online at the same time? So that is a strong assumption that it's independent trials, but it's used a lot to model real-world phenomenon. The binomial assumptions. How do you know it's a binomial situation? There's n independent trials taking place, success, failure on each trial. The probability of success in each trial is the same. It stays constant P. And your interest is in the total number of successes in the n trials. As an example, assume the probability that a randomly selected student receives no financial aid is 25%. The college administration surveys students until they find one not on financial aid. With the random variable x denote the number of students surveyed. Is x a binomial random variable? And the answer is no. It's not pre-specified. To be a binomial, you have to pre-specify how many trials you're going to do. Here we're going to interview until we find one not on financial aid. Essentially, this question is saying, how many times do you have to flip a coin until you get ahead? So you don't know a priori how many times you're going to flip it. How many times do I have to do something until I see a success? This is not a binomial. Technically, if you're curious, this is called actually a geometric random variable. Number of times you have to do something until a success, but it's not a binomial random variable. Another example. Unknown to the quality control inspector, the defect rate of light bulbs is 3%. The inspector selects 5 bulbs at random. With the random variable x denote the number of defective bulbs in the inspector's sample. Is this a random variable, binomial random variable? And the answer is yes, it is. And it's specified. We're saying the defect rate stays constant at 3%. We're interested in the total number of defective bulbs in the inspector sample. One thing that sometimes is helpful for people when they do binomial random variable problems is to write on the paper what success is. You could always frame it the other way. You just have to make sure your probability is correct. So here, success is actually a defective bulb. And we want to know how many successes we have in 5 bulbs. That's how many defectives we have in 5 bulbs. So in this case, success equals a defect. And so you don't get confused by it. Success sometimes may not be what you think success is in the binomial setups. The notation we use is we say x is, that tilde means x, is x is a binomial random variable with parameters n and p. N is the total number of trials. P is the probability of success on each trial. Now, we usually use the computer. We use R to find binomial probabilities, but there's some we can sort of do by hand. We call those the endpoint probabilities, successes. And so let's look at what they are. The probability of all failures. So that's the probability you fail in the first one, you fail in the second one, you fail in the third one. And that's the same as this. Why? Independence. So because of independence, the joint probability is going to be the product of these individual probabilities. And it's going to be the probability of failure to the n power. Why? Because we're assuming the probability of failure stays constant. The probability of success stays constant. And this is simply going to be 1 minus p quantity to the n. So the probability of all failures is 1 minus p quantity to the n. That was easy. Now the probability of all successes. You win, you win, you win, you win, you win. Because of independence, you get this. Because we assume the probability you win is constant in each trial, it's going to be probability win to the n. And that's just simply going to be p to the n. So p to the n is the probability of all successes. Quantity 1 minus p to the n is the probability of all failures. And very easy to do. So let's see. Suppose that 30% of the citizens of Somerville are opposed to joining Cambridge to form the new hipster paradise, Somerbridge. These are two, Somerville's the city right next to Cambridge. If a random sample of 7 adult residents of Somerville were selected, what's the probability that none would be opposed to joining Cambridge? So 0.3 is opposed, 0.7 is not opposed. That'd be 0.7 to the 7. All would be opposed. That'd be 0.3 to the 7. So very easy to find all successes and all failures. There are two more rules. From the complement rule, if you take the complement of all failures, it's at least one success. And the complement of all successes is at least one failure. So we actually get 4 probabilities we could easily do by hand. There's p to the n, 1 minus p to the n, 1 minus p to the n, 1 minus p to the n. Looks absolutely weird, but p to the n is probability of all successes, all failures. We're negating all successes. This is at least one failure. We're negating all failures. This is at least one success. So pretty straightforward. Assume that 30% of citizens of Somerville are opposed to joining Cambridge to form the new hipster paradise, Somerbridge. If a random sample of 7 adult residents of Somerville were selected, what's the probability that at least one person would be opposed to joining Cambridge? That's 1 minus probability no one would be opposed. That'd be simply 1 minus 0.7 to the 7th. So easy to do. Well, how do you find other binomial probabilities? You have to learn how to count. So suppose you have 3 friends, and each of them, without consulting the other 2, decides daily to wear caps with probability 0.3. You're about to meet 3 of them for lunch. X is the number of your friends wearing caps. You want to figure out the probability. Well, we know X can only take on the value 0, 1, 2, and 3. X is the number of friends wearing caps when you have 3 friends. So none of them are, all of them are, 1 is, or 2 is. We know that probability X equals 0 is 0.7 cubed. That's no one's wearing a cap. We know probability X equals 3 is 0.3 cubed. That's the probability that everyone's wearing a cap. We want to find the probability X equals 1 and X equals 2. And we actually say, do we need to find both of those probabilities? No, because all of them sum to 1. So we need to find one more. And then once we get one more probability, we can find the last one because we know they all have to sum to 1. Well, if we look at this, let's learn how to count. We want to find the probability X equals 1. That's the probability one friend out of 3 is wearing a cap. So it could be the first one is, the next 2 are not. The first one's not, the second one is, the third one is not. The first one's not, the second one's not, the third one is. There's 3 different scenarios for how you can have one person out of 3 wearing a cap. The probability that one person out of 3 is wearing a cap is going to be this, or this, or this. And we just add them up. So the probability X equals 1 is going to be the probability that's the first scenario, plus the probability it's the second scenario, plus the probability it's the third scenario. Each scenario has exactly the same probability of happening. You have one person wearing a cap, 2 people not. So it's going to be just the same thing 3 times. And we find that the probability X equals 1 is simply going to be 3, the number of scenarios possible, times 0.3, that's the probability of one person wearing a cap. 0.7 squared, that's the probability of two people not wearing a cap. This part is actually pretty straightforward to figure out. This is the hard number. That's how many ways one person out of three can wear a cap. In general, it's called combinatorics. It's combinations. And we have this thing called n choose x. So we refer to this as n choose x. It's the number of ways you can have x successes out of n trials. So 3 choose 1 was the number of ways you could have one person wearing a cap out of 3 friends. And from that, you get the binomial distribution formula. This is what the dbinom command in R is doing. The probability x takes on a value little x is simply going to be the combinatoric formula, p to the x, 1 minus p to the n minus x. And if you look at this, what does x plus n minus x equal? X plus n minus x equals, and you can do that. So this tells you I want x successes, n minus x failures. I've specified all n different outcomes. So that's called the binomial distribution formula. And again, the first thing is saying the number of ways you can have little x successes out of n trials. The second one is the probability of little x successes, probability of n minus x failures. And as we just said, x plus n minus x equals n. And we have to say what's happening on the n trials. So example, you sell 70% of people choose chicken sandwiches, the rest choose veggie sandwiches. What's the probability of selling 7 chicken sandwiches to the next 10 customers? We're going to assume independence of all the customers. 10 choose 7, 0.7 to 7, 0.3 to 3. You work it out, it's 0.27. These are easily done in R. The command dbinom computes the probability x equals little x. The command pbinom computes the probability x is less than or equal to x. As an example of this, the Jordan Sports Equipment Company finds that 10% of general adult population is left-handed. If 20 adults are randomly selected, what's the probability exactly 3 are left-handed? What's the probability that less than 6 are left-handed? So if x is the number of people in a group who are left-handed, x is binomial, n equals 20, p is 0.1. We want the probability x equals 3. You can do it by hand or just call the computer, and that's what the call is in the computer. And I realize there's a typo here. This should be x and p and x and p. Sorry about that. The order actually does matter here. What's the probability x is less than or equal to 5? P binom. That simply gives you the probability x is less than or equal to 5. Another binomial example would be an oil exploration firm is to drill 10 wells, each in a different location. The probability is 0.1, that's a good well. The probability is 0.9, it's a bad well. Each well costs $60,000 to drill, but a successful well brings in $1 million. X is the number of good wells. X is going to be binomial 10, 0.1. What's the probability of losing money? We want our profit equation is 1,000,000x minus 600,000. Why? Each well costs $60,000 to drill, so that's $60,000 fixed cost to drill the wells. If it's a good well, we make $1 million. X is the number of good wells, so that's the formula for profit. Well, the probability of losing money is the probability of profits less than 0. That's you lose money, profits less than 0. Do a little math, that's x is less than or equal to 0.6, less than 0.6, x equals 0. Why? Because x takes on integer values. The only way x is less than 0.6 is if x equals 0. Because the next value of x after 0 is 1. So this is going to be x equals 0. You can actually just go to a probability calculator, figure it out, because we know n and p. And this probably turns out to be 0.35 or so. So pretty low probability. Nice little example of oil drilling using the binomial. Now, a little bit more involved is suppose you own a catering company. You hire temporary employees to act as servers from the local college. Local college students as help. Not being the most reliable employees, there's an 80% chance that any one server will actually show up for a scheduled event. For a wedding scheduled on a given Saturday, you need at least 5 servers. So if you schedule 5 employees, what's the probability that all 5 come to work? So we want the probability x equals 5 when n is 5 and p is 0.8. That's a pretty low probability. So if you want to make sure we have 5 workers show up, we need to schedule more than 5 workers. If you schedule 7 employees, what's the probability that at least 5 come to work? So we want the probability x is bigger than or equal to 5. Look what we did here. It's 1 minus the probability x is less than or equal to 4. So pretty tricky, but the negation of x is less than or equal to 4 is the probability x is bigger than or equal to 5. So it becomes a pretty high probability. If we schedule 7 employees, we'll have at least 5 show up to help us out. The binomial distribution has some nice characteristics. The mean is n times p. Essentially, if you're an 80% free throw shooter, you shoot 100 free throws. On average, you expect 80 to go in. The variance is np times 1 minus p. Q is 1 minus p. And the standard deviation is square root of that. So pretty straightforward stuff. As an example, Derek Jeter supposes is a career 324 hitter. If he comes up to bat 100 times, he should get about 32.4 hits. It's np times 1 minus p. Same logic. The variability is given by this, and standard deviation is just the square root. One interesting thing about the binomial is it is skewed depending on what p is. If p is 0.5, it's symmetric. If p is 0.1, think about what that means. If p is 0.1, low probability of success, high probability of failure. P is 0.1. You're not going to have a lot of successes. You're going to have a lot of failures. You're skewed to the right. Most of your probability is on the left-hand side. And I didn't draw it, but if p is 0.9, what do you think it looks like? The opposite. This would be low, and these would be higher. And you'd be skewed to the left. So if p is low, you're skewed to the right. If p is high, you're skewed to the left. And then if p is 0.5, you're absolutely symmetric. So I hope you're having a great night, and that was a little journey into the binomial distribution. And next, we'll take a look at the normal. Take care, and hope to see you around in class.